Okay. On to number 37. What is the skeleton structure for this molecule? So it looks like we have 1, 2, 3, 4, 5 carbons in the long chain. So let's go ahead and draw that. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. And it's on the second and second to last carbon. So the answer is D. Remember, carbons and the hydrogens that are attached to the carbons don't need to be written out in skeleton structures. 37 is D, yeah. (38) based upon the functional group in the circle, what class of organic compound does this molecule belong to? So here's the functional group, and we have an OH and a double bonded O. So remember, that is a carboxylic acid when you have both of those together, both an alcohol and a aldehyde together, even though they're not alcohols and aldehydes, they're carboxylic acids since they're together. Based upon the functional group in the circle, what class? So again, we have OH in the circle. When it's just OH by itself, it's going to be an alcohol. And I think you actually have a table down here. Yeah, so you can always use this table in the back if you aren't sure what something's called. So now we have a double bonded C to an O, and then the O is attached to two R groups. So it's, and I'm not sure what that's called, so let's look at our table down in the bottom. Let's see. So we have our, there we go. So that's an ester, it looks like. And urea, so we have NH2, sorry, that should be a C, R. That's just how that is supposed to, but the R just means some other carbon-based structure, I guess. Urea carries ways to identify the functional group, so we have NH2 and a double bonded O. NH2 and a double bonded O, so that looks like an amide. What is the particular sequence of amino acids of a protein that are joined together by peptide or amide bonds called? Okay, remember when you have your amino acids, the connection of the amino acids is called the primary structure. The secondary structure is when you have the alpha helix and beta pleated sheets. The tertiary structures is when all those fold up into the 3D shape, and then the quaternary is when multiple amino acid chains come together to form the full protein, and not all proteins have a quaternary structure. The side chain is not capable of hydrogen bonding, so remember, hydrogen bonding is NH, FH, or OH. So we have NH that can hydrogen bond. CH, remember, that's no hydrogen bonds there. There we have an alcohol, so that works. And we have our H2 there attached to an N, so that works. So B is our answer. Two strands of a DNA molecule are held together by A, hydrogen bonding. That's something I guess you kind of just know. Hydrogen bonds are what hold it together. It's not going to be covalent bonds because that would take too much energy to break. You need to be able to break them easily to run for the DNA to like replicate and be used. Ionic bonds, those are too strong too. And then there are no ions in DNA. And those would probably be, those are a bit stronger too. But yeah, hydrogen bonds. So they're strong bonds, but they're not strong enough. They're strong bonds that are present in DNA, but they're not so strong that they can't be broken. They're easily breakable. Proteins are composed of amino acids that may form an amine bond through the reaction shown. In this reaction, what acts as the Lewis base? Okay, so a Lewis base, remember, is going to be, it's going to be our electrophile or our nucleophile. A Lewis base is our 45, is going to be our, I'm going to Google it because I can't quite remember. So our Lewis base can donate an electron pair. E minus donor, which makes it a nucleophile. And I had to Google that, which I guess, yeah. So that's something you'll want to remember for the exam. But the electron donor, it's a nucleophile. So we know molecule 2 we can see is donating that electron pair to the carbon. And that makes molecule 2 our Lewis base. Imagine that you are making a solution in a volumetric flask. Oh, this is like our badges. So as you add water above the flask and it goes past the calibration line, what should you do? Okay, so remember, when it goes past the calibration line, you can't take out any solution because you'll be taking out both the solution and the water. So that's not going to work. So you can't use a medicine dropper. The solution's going to be wrong, so you don't want to use it like you've made it. So you'll want to pour out the whole solution, because if you add a tiny bit more solute, you're not going to know how much to add. So you'll just have to start over if you mess up like that. In the final lab, you carried out biologically. I don't think you did this, but why were you adding NaCl to the water? So I think you are doing that 47, is that C? Okay. So the answer is C, because I have the answer. But also, yeah. Basically, when you add the NaCl, since you have a bunch of charges, it messes with the proteins, and so the protein structures, I guess, so it causes them to unfold. And then when they get all unfolded, they get all tangled up, so they come out of the solution. But like I said, I don't think you guys did that lab. What is the molarity of a sodium chloride solution from 5.84 dissolved in... Okay, so 5.84 grams times 1 mole of NaCl for every 58.44 grams, right? So then we get mole of NaCl. And then we'll divide it by, we want to know per milliliter, per 802 milliliters. Then we have to convert that to liters, because molar is moles per liter, right? So times 1,000 milliliters per liter. Then we'll multiply that all out, and we get B. There we go. How many milliliters of 0.502 molar acetic acid solution contain 0.120 moles of acetic acid? So we have 0.502 moles per liter times X liters is equal to 0.120 moles, right? So let's divide. We're basically trying to solve for X. So we'll divide by, basically we're just times X. So we'll divide both sides by 0.502 moles. And then we get 0.120 divided by 0.502 is equal to X over liters. So this is going to be in liters basically. And then we'll have to convert it to milliliters, so times 1,000. And for that you get D, 239 milliliters. $50 in lab near the end of the semester. Synthesized luminol, that was towards the beginning semester. How did you know the reaction occurred? Remember, there was light. That was the one that glowed. And that was C is the answer for that. Extra credit. So based on the following, so this is where we're strongest reducing versus weakest oxidizing, etc., etc. So when Z is placed in solution of X plus, there's no change. So we know that X is going to be a stronger than Z, a stronger reducing agent, right? V is placed in the dark residue form, so we know V is greater than Z. Z is placed in Y, so we know Z is greater than Y. And when X is in V, it doesn't change. We know V is greater than X. So we know V is greater than both X and Z. And we know X is greater than Z. We know Z is greater than Y. So VXZY, 51 is A, VXZY. Okay. So basically we know Y was always the least. Yeah, basically just go and using all of these four equations you can figure out what order they are. Which of the following substances will exhibit dipole-dipole intermolecular forces? So dipole-dipole, remember that means there has to be some polarity. CH4 doesn't have any polarity. CO2, remember that's a straight molecule, no polarity there. F2, they're both equally, even though those are both electronegative, they are both equally pulling on each other. And AR, that's just a single atom, so there's no polarity there. And we know that H2O forms hydrogen bonds, which is a type of dipole-dipole intermolecular force. So we'll go with B on that. Which intermolecular force is responsible for the density of H2O being less than the density of H2O liquid? So solid versus liquid. So water is super cool, remember. It can hydrogen bond. And basically when it hydrogen bonds, all those hydrogen bonds make a kind of a matrix that gives it that crystal pattern that makes H2O ice bigger than water. Identify the functional group. So you have a double bonded O to the C at the end of the molecule. That is going to be a carbonyl group, because it's not a ketone, it's an aldehyde, so we'll go less specific there. And I'm going to go on to the free response in the next video.